Over the last few years, MotoGP motorbike aerodynamics has gotten a lot more interesting. That's because while traditionally around the front bottom, these motorbikes were quite smooth and motorbike looking, now they put ducts on them that supposedly help them produce useful aerodynamics during the race. Whether these ducts are generally beneficial or not, and how to optimize them, are still major unknowns because this is quite new tech. And motorbike aerodynamics are arguably even more complex than race car aerodynamics because a motorbike's attitude changes throughout the circuit. On the straights, not only is the bike upright, but the rider is hugging the bike and trying to reduce the frontal area. But then in the corners, the bike is now tilting at extreme angles to like over 60 degrees, and the rider is almost falling off of it. And then when the rider is braking, usually he sits upright to increase the drag through the frontal area. So all of these geometric changes means that a flow control device like these ducts may not always work and may actually, under certain circumstances, hinder the bike's performance. So how do these ducts work? When are they most effective, and are all geometries effective? That is what we're looking at today. And to do so, we're looking at this paper here, which is called Aerodynamic Study of MotoGP Motorcycle Flow Redirectors. And that last term, flow redirectors, is what these bikes are called in a technical way. So you can see them in figure 8 if we scroll down here. Here is figure 8, just up here. So we have on each side of these bikes down below, we have two devices. One here, oh, there's actually one up here and one down here. The lower ones are the flow redirectors that we're looking at. So you can see that depending on the bike, this flow redirector is quite different. Sometimes it is larger, sometimes it's sucked more into the bike, sometimes it's rounder, sometimes it's more square and rectangular. So like in these different figures here. So do all of these work? Well, let's find out. So according to some studies, the most important parts of a motorbike, at least from a drag point of view, are the fairing, the front wheel, and the suspension. That makes sense because all of these objects are really in the front of the motorbike and are hitting free stream flow most of the time. And the desired aerodynamics of a motorbike during the race is quite complicated. So for example, during acceleration, you want to reduce the frontal lift so that you reduce the chances of doing a wheelie. That also allows you to put more power down to the road. And to aid that power transfer, having more downforce on the rear is also a good thing because that's where the power is going into the road. And like F1 cars, when you are at high speeds, you don't want so much drag because that will slow you down. And then through corners, you don't want lateral force pushing you out of the corner because that reduces how fast you can make it around the corner. So in terms of the flow redirector, the general idea is that it is mounted quite low on the bike and at the front. Around here, just here, this red bit here, and this red and blue bit here. You can see it's kind of the outlet here. So this duct, this flow redirector, it redirects air from around the front and into the lower region of the motorbike, which is a little bit surprising. So you actually get air sucked in here and then it pushes it down and underneath the motorbike. So importantly, the air to the redirector is larger than the area, to the inlet is larger than the outlet. So that means that from basic aerodynamics, we can tell that the flow exiting the redirector will be faster than when it is entering. Now, when a motorbike is leaning into a corner, because the side of the motorbike gets so close to the ground, the lower part of it is effectively like a diffuser. So that's insane. In figure 9 here, we see that this motorbike is leaning so much that it creates a low pressure zone underneath this lower part and increases downforce. So it's effectively like this dynamic diffuser. So from this general effect, a question arises as to whether the flow redirectors aid this process or not. So to see if the flow redirector can do that or not, and its general flow physics and effects on the motorbike, the researchers did a CFD simulation on a motorbike and looked at different flow redirector shapes to see if they all had the same effect or if there were some deviations. So the 3D model of the motorbike can be seen in figure 12, if I scroll down here. And this is based on the 2022 MotoGP regulations. So it looks really good, but one limitation to this CAD model is that when the researchers were looking at the straight travel of the motorbike compared to cornering, they didn't change the rider's position. You can see here that this rider is hunched over and he's really clutching the steering wheel and the bars and the fuel tank. So the researchers said that this position of the rider has been shown to affect the aerodynamic performance of a high up on the motorbike, the surfaces high up on the motorbike. And they argued that the flow redirector is not close enough to the rider's limbs, so that the rider's position wouldn't affect the flow redirectors during the cornering. So they effectively conclude that the effect of the rider's position on the flow redirectors is negligible, therefore they didn't have to change the rider's position. So while I understand that logic, when considering the direct effect of the rider on the flow redirector, but there might be some indirect effects. So for example, perhaps the position of the rider changes the pressure around the middle section of the motorbike, which then changes how much the flow underneath the bike will stay under the bike or bleed up into the middle section. This is also an indirect effect and could be important. However, given that this paper seems to be one of the first papers looking at this flow redirector aerodynamics, and hence there isn't too much to build upon from other works, looking solely at the direct effects is still very useful for us to understand how they work. So overall, they looked at how the addition of the flow redirector affected the bike's aerodynamics, but they also looked at, in figure 8, for example, the beta angle. So if I come up to figure 8, this beta angle is really how much the flow redirector is fanned out, how much it flares out to the sides, and how quickly that happens. They also looked at how the angle of the inlet, so alpha here on figure 8b, affects the flow redirector's aerodynamics. And this is really how much the inlet is angled to the free stream flow, whether it is flush to the free stream flow, so it's perpendicular, or whether it's more angled, so it's not perpendicular. So in figure 15, we see the size of the CFD domain, if I come down here. So it's really quite big. The inlet is set 4 motorbike heights upstream. The outlet is set 10 motorbike heights downstream, which is reasonable. It gives enough time for the weight to evolve. And the sides were 3 motorbike heights from the motorbike, and the top was 6 motorbike heights away. And this was based on literature. So one thing to note is that when the bike was leaning, the entire domain was simulated. And that is because the geometry is no longer symmetric around the free stream plane. But when they looked at when the motorbike was straight up, then they only simulated half the domain. That is because they say that the bike is symmetrical about the free stream plane, so they can get away with it. I'm not sure how much that would change the results, because you still have a bluff body, and bluff bodies don't simulate that well when you start putting in symmetry planes, because the flow is inherently periodic and not symmetric. So in terms of the boundary layer mesh, this is an interesting approach that they have actually. So they use the K-Omega SST turbulence model, which gets my thumbs up. But for the Y plus value, they went for 50. Now, this is not wrong, because the beauty of the K-Omega SST turbulence model is that it can handle Y plus values from less than 1 all the way up to hundreds, because it just toggles on whether you're using the omega or the epsilon equation. But personally, if I had the choice, I would prefer to keep the Y plus low, like below 5, because ideally, and below 1 ideally, because when you go above 20-ish, most CFD softwares will now toggle on Wolf functions to predict what is happening in the boundary layer region, this lower part. Personally, I don't like that, because a turbulence model is already a little dodgy to begin with, and Wolf functions are usually even dodgier. So a low Y plus is better, and also from the point of view that you have a finer resolution in this lower boundary layer region. So you don't just have one massive cell encompassing this large part of this very important part of the boundary layer, but instead you break it up into sections to get more accurate gradients. But all that depends on how many cells you can use, really. So we'll see in a second their grid convergence study to see how many cells they could get away with, and maybe there was a limitation there. But quickly, I'll just mention here that they are using OpenFOAM, which is a really good and free CFD software. And if you want to learn how to use OpenFOAM, check out our courses in the link below. We have ones that take you from the very start of how to use it, from even how to install it, all the way to running DES simulations. We also have a course on advanced meshing that covers in detail sliding meshes, dynamically morphing meshes, and even overset meshes. You can find that in the link below. But back to this podcast. So in table 5, we see the grid convergence study, and they considered 3 meshes. The coarsest mesh had 6.3 million cells, the medium mesh had 8.9 million cells, and the finest mesh was 13 million cells in this table here. They chose to go with the medium mesh because the drag coefficient was almost identical to the fine mesh, which is really quite a feat. I mean, it was like really, really close, within like 0.1%. That's really amazing. So in this CFD study, 8.9 million cells were used, and that gives us insight into why maybe they decided to use a half model for the motorbike when it was upright, and maybe why they didn't have a finer Y+. So 8.9 million cells isn't that much, but maybe they didn't have the resources, I don't know. But anyway, for some reason they said that they had to select just one velocity at the inlet boundary condition for both when the bike was upright and leaning. I don't quite understand why they needed to do that, because they themselves say that these two bike orientations correspond to two completely different performance situations. Nevertheless, they chose only one speed to do when the bike was upright and leaning. They say that a speed of 180 kilometers per hour, so 50 meters per second, was chosen because at this speed, the rider could be exiting a corner and straightening up, and also going around a fast corner. So I don't know about you, but riding a bike around a corner at 180 kilometers per hour would be insane. I haven't ridden track bikes, but going around a corner at even 90 kilometers per hour on a dirt bike is definitely thrilling, to say the least. So anyway, the velocity is 50 meters per second. So one really good thing that they did was that they specified the ground to be a moving wall at 50 meters per second, which is a good idea. The reason why is because if you don't do that, then you get a boundary layer forming and hitting the bike, which isn't what happens in real life, unless there is a wind, of course, but still, it's not that big. So the wheel rotation was simulated with a rotating wall boundary condition. This is really a subpar rotation method. If this was 20 years ago, then you would be fine, but now it's not adequate. So that is one weakness in their CFD so far. But let's quickly discuss the options that they had. So to begin with, they did a RANS simulation, which means that they can't have a sliding mesh because this is steady state. As such, they can only really choose between rotating wall and MRF. Of the two, the MRF is usually more accurate, so the rotating wall isn't that great here. So the Thomas density of the flow was 1%, which I quite like that they went a little higher here. In fact, I would have liked an even greater number because that's what happens in real life as well, with the wind and etc. But nevertheless, this value is better than what is used in most automotive CFD. So let's move on to the validation now. So in table 9, if I scroll down here we go, table 9, they show the drag coefficient areas of a Honda RS500, another CAD model of a motorbike, and their design. They don't seem to say just how similar to or different these models are from each other. We can see the figures here, and clearly there are some differences. One major difference is the front fender, so around here, and also the windshield. So they vary a little. They say that their CFD is validated because this is within 4% of other CAD models. I'm not sure how good this validation is then. I mean, if the models are different, geometrically speaking, then you can't really compare them that much anyway. So up until now, the CFD was pretty good. There were only two major weaknesses. The first being that they only simulated half the motorbike when it was upright. The second was the rotating wall boundary condition. They had a good grid convergence, but here the validation process I think is pretty bad. So for that reason, I would rate their CFD perhaps around a 6 out of 10. So let's move on to their design of experiments. And the reason why they did a design of experiments is to see how the different geometric features of the duct affected the performance of the motorbike. So in table 10, they show the different flow redirector configurations that they tested. They did a Taguchi method, which effectively looks at the extreme combinations of the parameters of interest. So let's move on to the results now. In table 11, we see the effects of the wheel rotation on the lift and drag coefficients of the straight up bike. And this is a little worrying because in the automotive industry, it is well known that the wheel rotation is a big deal. If you don't have wheel rotation, then the results do change quite a lot. And that's exactly what we see here in table 11. In fact, the effects of the wheel rotation on the drag coefficient is actually smaller than I expected. It is only increasing the drag coefficient by about 2%, or reducing it, sorry. But the lift is greatly affected. With the wheel rotation, the lift coefficient increases by 21%. That is alarming because the rotating wheel boundary condition isn't that good. So I'm wondering how accurate the lift coefficient results will be, and how much would an MRF approach have changed the lift coefficient. And things get even more interesting in table 12 because, okay, again, the rotating wheel boundary condition dropped the drag coefficient by only 3%, but the lift coefficient increased by a massive 36% when the motorbike was leaning. This tells us that when the bike is leaning, the aerodynamics is more sensitive to the wheel rotation. That's quite an interesting fact. So I think that for the lift coefficient, we should look at the results with caution. For the drag coefficient, I think that if the results show more than a few percent change, then we can probably trust them. So let's move on to the results now. In figure 18, we have a bunch of pictures for the upright motorbike, this figure here. Let me zoom out a little bit so we can see all of them. Okay, here we go. So let's focus on the right column because this is with the wheel rotation. The left column is without wheel rotation, and I'm not really sure why they did so many simulations with this stationary wheel, because that's not really a thing in racing. Like, you don't go around with the wheel stationary. So doing so many simulations doesn't really make much sense to me. But anyway, a few would have been good enough to look at. So anyway, in figure 18b, for example, the flow is directed down quite a lot with these flow redirectors, and a vortex is formed in the process. As you can see here, the vortex is forming down here. This general trend holds for all the other flow redirector configurations in figure 18. They will have this redirection of flow going on here. But some seem to be better at funneling air down and more cleanly than others. For example, in figure 18F, which features a flow redirector, which is when the flow redirector is not flared and it's angled to the free stream more, so the inlet is angled up, it's a lot more messy, the flow. So it's not entering the inlet nearly as well, I think. So in figure 19, we see the pressure coefficient plots along the bikes. In figure 19b, for example, we see the green lines show the bike with the redirector, and the red line is without. The redirector greatly reduces the pressure coefficient around the front of the motorbike and even around the front wheel. This shows more downforces being generated in this location. Now, under the motorbike, the redirector isn't doing too much. However, you can see all these lines are pretty much on each other. So perhaps when the motorbike is upright, the redirector doesn't do much to the back half of the motorbike. These trends hold for the other redirector configurations as well. As you can see here, they're all showing pretty similar things. Looking at table 13, we can see that with all the flow redirector configurations, the changes in the drag coefficient hover around 4 to 5%, or maybe even a little bit less than that as well. This is borderline in the uncertainty of the CFD. So I don't think we can conclude that when the motorbike is upright, the redirectors are really changing the drag coefficient either way. It's within this error here. So I guess that can be seen as a good thing because it isn't making the drag much worse, at least. As for the lift coefficient, there are some changes up to 30% being seen here. And perhaps these larger changes are trustworthy, but even then, it means that the flow directors are having a very varied effect on the lift coefficient of the motorbike when it is upright, depending on how this redirector is modeled. So that means that you have to be careful when designing them. So what about when the bike is leaning though? So in table 14, if we scroll all the way down here, we see the lift and drag coefficients, and pretty much all configurations, the redirector is greatly reducing the lift coefficient by about 60 to 70%. So you can see 65, 75, 83, 75% reductions. These differences, I think, are outside the errors of the CFD. So it seems like these redirectors are really good at reducing the lift coefficient of the motorbike when cornering and you're in this leaning position. So from these results so far, the redirectors are performing better during cornering when the rider is leaning than on the straights. Let's now move to the sensitivity study, so the Taguchi method with the DOE, and to see how different geometric features affect the redirector's effects on the lift coefficient. So in figure 24 here, we see that by far, the motorbike lean has the greatest effect on the redirector lift coefficient effects. And we can see quite clearly that just from the results from before, leaning the motorbike greatly reduced the lift coefficient. We didn't need to do this sensitivity study, I guess, to see that. It was so prominent. And comparing that parameter to how much the redirectors flared out, so alpha and beta, and the angle of their inlet, these ones didn't really affect the lift coefficient that much. So flaring the redirectors out more or making the inlet more angled to the flow, to the inlet, to the free stream flow at least, didn't have that much of an effect compared to the motorbike lean. That was by far the most important parameter. And also, looking at the drag coefficient, again, the motorbike lean was the most important parameter and by a long way. Like the other factors had almost no effect by comparison. It was like a 10-to-1 difference. So with that, we come to the end of this podcast. The general conclusion is that the redirectors of any geometry really are good at reducing lift during the corners. on the straights, their effects are largely unclear because of the uncertainty in the CFD. But let's say that they do increase the drag coefficient during the corners anyway. Well, that isn't such a bad thing either, because that helps the rider decelerate quicker, which means that you can carry more speed into the corner and brake later. That will result in you going around the corners faster. So this is one time really where we can draw quite conclusively universal conclusions that the effects of these redirectors was largely enough to override the error in terms of lift coefficient, and they are beneficial when you are leaning. In terms of the drag coefficient, okay, we can't really tell too much about that. And on the straights, okay, the redirectors may not be affecting the flow that much. So if you like this podcast, hit the like button, and if you want to see more like this, hit the subscribe and or the follow button, whichever platform you're on. And if you want to learn more about open foam and or get better at CFD, check out our courses in the link below. And in that Atmosphere Hawk link below, you'll find some information about why in most aerodynamic experiments, there is a 2 to 4% uncertainty and you don't even know it. So there's the math presented there. So that is the end of this podcast, and I'll see you next one. Peace out, amigos.